Okay, so welcome back to the second days of our hybrid conference this year. So today the first speaker is Vincent Guedj from Toulouse, and he's going to talk about singular Kaehler-Einstein metrics.
Thank you very much, Filippo, and thanks also to Claudio and Adriano for organizing this conference. So the plan of my series of talk is as follows. I will try to motivate a bit the problem of classification of compact Kaehler varieties, also discuss the problem of the construction of canonical Kaehler metrics on these mildly singular varieties. And then in the final lecture, I will explain a recent method to construct and study weak Kaehler-Ritchie flows. So there will be a connection, obviously, with the lectures by Valentino. And the precise plan of the three lectures is as follows. So in this first lecture today, I will explain in a survey type lecture on the problem of the solution of singular and construction of singular Kaehler-Einstein metrics. Tomorrow, I will focus on a specific problem, namely the proof of a celebrated L infinity a priori estimate, and I will provide you with a very recent proof that we have devised with Guangqing Lu from Orsay. And then in my last lecture on Friday morning, I will survey a bit the so-called Sontian program, which aims at using the Kaehler-Ritchie flow in order to both classify algebraic or Kaehler varieties and construct at the same time canonical Kaehler metrics. Okay, so that's the plan. And let me start by a rather famous problem, namely the Calabi conjecture. So in the sequel, X will denote a compact Kaehler manifold of complex dimension n, and omega is a Kaehler form. So as Valentino recalled yesterday, Kaehler form is a 1-1 form that is both smooth, positive, and closed. So locally, you can write it in local homomorphic coordinate like this. And locally, the Ritchie curvature form of this form omega is then defined by this formula, which Valentino motivated in his lecture. And the normalizing constant is so chosen that this Ritchie form, which is here locally defined but makes sense globally, is a closed 1-1 form that represents the first Chern class. So although this formula in blue is local, you have an important global relation between two Ritchie forms. So if omega prime is yet another Kaehler form, then the Ritchie curvature form of omega prime and the Ritchie curvature form of omega are related by the fact that their difference is given by minus the normalized IDD bar of the log of the ratio of the volumes of these forms. So here in the sequel, D is the standard differential operator, and DC is this normalized twisted version of D minus D bar. And the constants are chosen both so that these two operators are real, and so that DDC is I divided by pi DD bar. Okay, so as Valentino explained yesterday, if you pick a Kaehler form omega, then the reach of omega is a 1-1 form closed that represents the first Chern class. So many years ago, more than half a century ago, Calabi asked about the converse. So if you fix eta, a closed differential form which represents the first Chern class, can you find omega, a Kaehler form, whose Ritchie form is equal to eta? And this problem has remained open for more than 2 decades until Yao solved it positively in the late 70s. And let me explain a bit how this is connected to complex Monge-Ampère equations. So this problem can be reduced to solving a complex Monge-Ampère equation, CMAE, in this shorthand. Namely, we fix alpha in the H11 cohomology group, a fixed cohomology class, Kaehler class, and pick omega, a Kaehler form in alpha. Then let's pick also a smooth representative of the first Chern class. Then, as I explained earlier, reach of omega is homologous to eta. So yesterday in his lecture, Valentino told you about the fact that on Kaehler manifolds, there is an important lemma, which is called the DD bar lemma. So reach of omega and eta are not only D cohomologous, but they're also DDC cohomologous. So we can find a smooth function H so that reach of omega is equal to eta plus DDC of this function H. So now we seek for omega phi, which is a perturbation of omega, representing the same Kaehler class. Omega phi is omega plus DDC phi. And we seek for such a function phi so that reach of omega phi is equal to eta, so in order to solve the Calabi problem. So now, if you remember that reach of omega phi and reach of omega are related by this global equation, then asking for reach of omega phi to be equal to eta is equivalent to the fact that the DDC of H minus log of the ratio of the volume is equal to 0. And now I'm going to use the fact that the manifold X is compact, so there is no harmonic function on X but the constant. So this function inside the bracket is constant, and therefore the problem that we are interested in is equivalent to solving this equation, omega plus DDC phi to the n is equal to e to the h plus some constant, normalizing constant, c, times omega to the n. And this is a complex Monge-Ampère equation, and one can go in the opposite direction, namely if you can solve this equation, or this equation is really equivalent to solving the Calabi problem. So this is precisely this equation that Yao has solved in the late 70s. So we adjust the constant c, so we normalize h so that this mass condition is satisfied, and if such is the case, then the constant c here turns out to be equal to 0. And what Yao did is to solve the following Monge-Ampère equation, namely, given this normalization, Yao showed that there always exists a unique smooth solution phi to this complex Monge-Ampère equation in such a way that omega phi is a Kaehler form, and moreover, the potential phi is unique up to the addition of a constant. Okay, the proof of this important and fundamental result will be I guess, given by Valentino in his second lecture this afternoon. So what I will insist on tomorrow is in presenting the one step of the proof by Yao, and actually a generalization of it, which has been very influential, and which is the a priori L infinity estimate. So this is only step of the proof that I will explain tomorrow. And I guess that Valentino is going to say a bit more words about the remaining part of the proof. Okay, so let me go on and pass on to a slightly more general problem, which is the Kaehler-Einstein problem. So a metric omega, a Kaehler metric is called Kaehler-Einstein if there exists a real constant lambda, so that reach of omega is lambda times omega. As I said, reach of omega is representing the first Chern class of X. So there is an obvious cohomological constraint for this problem, namely C1 of X should have a definite sign. This is always the case for compact Riemann surfaces, but this is no longer the case in complex dimension 2 or higher. So for instance, if you take a product of compact Riemann surfaces, S1 and S2, then C1 of X has a definite side if and only if the two Riemann surfaces are of the same type. So either P1 and P1 are two elliptic curves or two compact hyperbolic Riemann surfaces. Note also that by definition, the Ricci form is invariant under scaling by a positive constant. So actually in this problem, there is essentially 3 cases to be considered. You can rescale the form so that lambda is either -1 or 0 or +1. So what about a solution to this problem? Well, this turns out again to be equivalent to solve a complex Monge-Ampère equation. So let's assume this cohomological constraint is satisfied. So C1 of x is proportional to the cohomologic class omega by a factor lambda. And let's speak, as previously, a smooth function h, so that reach of omega and lambda omega, which are cohomologous, differs from the DDC of a smooth function of this smooth function h. Then we seek again for a solution to the Kaehler-Einstein problem by perturbing omega, adding DDC of phi for a smooth function phi, so that reach of omega phi is equal to lambda omega phi. And if you plug in this global relation between the 2 Ricci forms, then again, the Kaehler-Einstein equation turns out to be equal to the fact that the DDC of this bracket is equal to 0. And again, x is compact, so there is this function has to be constant. So at the end of the day, you obtain the following complex Monge-Ampère equation, namely the volume of omega phi, so the determinant, if you like, or normalized determinant of the Hessian of the local potential of omega plus the Hessian complex Hessian of phi should be equal to this right-hand side, e to the minus lambda phi plus h times omega to the n, assuming that we have normalized the function h as we have done previously. So this, obviously, this equation contains the Calabi case, the Calabi conjecture as a particular case. So for lambda equal to 0, you get back the Calabi problem. So when are these families of complex Monge-Ampère equations solvable? Well, here are a few answers. So first, when lambda is -1, then one can always solve this complex Monge-Ampère equations. And Aubin and Yao answered this independently in the 70s. So this equation admits a unique smooth solution. And as a consequence, there always exists a unique Kaehler-Einstein metric if the first Chern class of the manifold is negative. For lambda equal to 0, so that's this celebrated result of Yao, if you assume x has a first Chern class 0, then in each cohomology class alpha, one can find a unique Ricci flat Kaehler-Einstein metric. So if you like, there are more solutions to the lambda equals 0 case, and there are as many solutions as you have Kaehler classes on your manifold. And much more recently, so almost 40 years after the works of Aubin and Yao, the solution to the case lambda equals +1 has been provided by a series of work by Chen, Donaldson, and Son. So if the first Chern class of x is positive, then one cannot always solve the equation. And the moment where one can solve them is provided by the following theorem. So the following are equivalent. One can solve this specific Monge-Ampère equation. And moreover, let me, for simplicity, say that only consider a case where it admits a unique solution, if and only if there exists a unique Kaehler-Einstein metric, if and only if, and that's the important part of the statement, the manifold X polarized by the anti-canonical bundle is uniformly k-stable. So I'm not going to explain what this means. Let me just abruptly say that the solution to this highly nonlinear PDE is equivalent, or the fact that one can solve this highly nonlinear PDE is equivalent to a certain algebraic condition, which is this uniformly case stability assumption. Okay, my goal now is to move on to the situation where the underlying space is no longer smooth, but rather a mildly singular algebraic or Kaehler variety. So let me first define this context and motivate it. So since several decades, the so-called minimal model program, MMP, has as main object to study the classification of algebraic manifolds up to birational equivalence. So for dimension 1, this has been known since the 19th century, and starting with dimension 2, this is well known that one can classify algebraic surfaces, let's say by works of the Italian school and the Russian school, and some completion by the Japanese school in the mid-20th century. However, starting dimension 3, the situation becomes incredibly more complicated. And it has been known since the 70s at least that one cannot hope and classify complex algebraic varieties in dimension 3 or higher without allowing for working with mildly singular settings. So the problem that I would like to discuss briefly in the sequel is what kind of singularities we need to work with, and what becomes the Kaehler-Einstein equation in that context, how this Kaehler-Einstein equation can be interpreted once again in terms of a complex Monge-Ampère equation, but that will become degenerate, hence the D in this abbreviation, and say a few words on various methods for how solving these equations. Okay, so first a few words about the singularities. The main type of singularities we are going to consider are the so-called canonical on one hand and log terminal singularities. So so the singularities we are considering are normal. So in particular, that's maybe the main point for you here, is that the singular locus of the variety is a complex variety of complex codimension, at least 2. And by definition, so formal algebraic definition, such a variety is called Q-Gorenstein if you can make sense of the canonical divisor as a Q-line model, and that's not the end of it. I want some further extra property for the singularities I'm going to consider. So let's take, by Hironaka's result, we can take a log resolution of the singularities. Then, so X prime here is a smooth model for the manifold X with the exception divisor has simple normal crossings. Then when I look at the corresponding adjunction formula, or the way this canonical bundle of the smooth model transform, well, it's the pullback of the canonical bundle of the singular model, Kx, modulo a linear combination of this exceptional divisor EI. So there are unique rational numbers AI, which are called the discrepancies with respect to this log resolution, so that this formula holds. And the definition of canonical and log terminal singularities from this algebraic point of view is as follows. So we say that the singularities are canonical if these discrepancies are non-negative. And we say that the singularities are log terminal if these discrepancies are allowed to be negative, but just a bit. So they should be strictly bigger than -1 for all I. And well, it's classical lemma in this context that if this holds for one log resolution, then this holds for any other resolution. So it's this notion is actually independent of the choice that you make of the log resolution. Okay, so if you're not an algebraic geometer and if you have never seen this definition, it's probably essentially difficult to understand. So let me give a few examples of what it is about. So first, starting dimension 2. If you start with a normal algebraic surface, then first the canonical singularities are actually equivalent to being quotient singularities by a finite subgroup of SL2C. And by comparison, log terminal singularities are again quotient singularities, but here you allow for slightly larger class of finite subgroups, namely the finite subgroups of GL2C. So in complex dimension 2, all these singularities that we're interested in are quotient singularities. And in particular, from the analytic point of view, we can do a no-before type analysis that would allow to extend Yau's works and Aubin's work in a rather reasonably easy way. This will no longer be the case in higher dimension. So in higher dimension, quotient singularities are still log terminal, but there are known quotient singularities. Let me give you a simple example. So pick H, which is a smooth degree D hypersurface in CPn plus 1. So H has a dimension n, and consider the affine cone over H. Then this cone has an isolated singularity at the origin, and this singularity is canonical if and only if the degree is not higher than n plus 1. And moreover, this singularity is not quotient, and maybe if you don't feel very comfortable with singularities, one basic and very important example you should keep in mind is this ordinary double part. So I write this down in complex dimension 4/dimension 3, but the same formula would hold in any dimension. So this ordinary double point is a canonical singularity, a very important and simple one, but it's not quotient singularity starting dimension 3. Okay, let me now formulate an analytic point of view on this on the log terminal singularities. So the canonical divisor is actually a Q divisor. So RKX is a line model, holomorphic line model. I pick a local holomorphic section of it. And I can form this sigma wedge sigma bar modulo a right power of I will be a volume form. So I raise this to the appropriate power. And this is a positive volume form, at least on the regular part of the variety. So here is an interpretation of what is a log terminal singularity. So if you work in the log resolution of the singularities, so you have this simple normal crossing divisor EI, and then when you pull back this measure mu sigma, what you end up with is a product of the ZI to the power 2AI. So let me maybe go back to the definition. So this formula, this type of adjunction formula that you have that defines somehow these singularities. So you see the sum of the AI, EI on the right-hand side. Well, an equivalent formulation, if you like, from the analytic point of view, is precisely what I'm writing here. That when you pull back this volume form, well, on the right-hand side, you have a smooth volume form time product of this local defining equation modulo square to the power 2AI. And therefore, the measure on the right-hand side, it has finite mass if and only if, obviously, the AI should not be too negative. So the right condition is that AI should be strictly bigger than -1. And so this is precisely the log terminal singularity definition. So to sum up, with this equivalent point of view provided by this lemma, the type of singularities that we are going to consider, these log terminal singularities, are exactly those singularities for which the natural volume form on our algebraic variety have finite mass near globally on the manifold and especially near the singularities. Okay, this was a local formulation, but this construction can be globalized. So if you pick a smooth metric of the canonical bundle, then you can construct a normalized version of this mu sigma. And this turns out to be independent of the choice of this holomorphic section. So this defines a smooth positive volume form on the regular part of the variety, and it has locally finite mass near the singular locus, if and only if the singularities are log terminal. Okay, what about? This was to explain what is a log terminal singularity. Now I would like to motivate a bit the notion of canonical singularity. So let me consider the so-called notion of manifold of general type. So this precisely means that X, so here X is smooth, and it is a compact Kaehler manifold whose canonical bundle is being. So being is a positivity notion. It means that if you look at the pre-canonical sections, as the power goes to infinity, you have more and more sections, so many that you can embed birationally X into a complex projective space of large dimension. From a metric point of view, the best positivity notion would be that Kx is ample or positive, so admitting a smooth metric of positive curvature. This is something that may happen, but that one cannot expect in general in high dimension. So B is the, if you like, the appropriate positivity notion in high dimension, which gives you the higher dimensional version of compact hyperbolic Riemann surfaces. So a very important algebraic result from a bit more than 10 years ago has been provided by Birka, Kashini, Heiken, and Makanon, saying that the canonical ring, so if you look at the ring generated by the spaces of holomorphic, pre-canonical holomorphic sections, this canonical ring is finitely generated. So you can construct the proj of this ring. This is the so-called canonical model. This is a model for the manifold X, and it turns out to have canonical singularities. So that's actually the reason why these singularities have been called that way. And on this model, the canonical bundle becomes ample. So it's probably a bit, I'm probably going a bit too fast here, but if you like, either you work on the smooth model X, but then the canonical bundle has a positivity property which is a bit difficult to work with, or you work on the canonical model, so a singular model for X, and then what you gain is that the canonical line model of this mildly singular model has the right positivity property, so is ample in the right sense. So now a natural question is, can we make sense of Aubin-Yao type metric in this context? And for that, I need to define the notion of singular Ricci curvature. So let X be, as previously, Q-Gorenstein compact Kaehler variety. And so I see the question in the chat. So if you are ample, if you are an ample line model, then you are big. But big is a bit more general. You, from a metric point of view, the first Chant class, you can find a metric which is non-smooth, but whose curvature form dominates the Kaehler form. That's a metric point of view on bigness. So you are big if your first Chant class, if you can find a metric, a singular metric, whose curvature form dominates the Kaehler form. While ample means that you can pick the same guy, but with the metric which is smooth. So I don't know if maybe not enough to answer your question. Maybe I can come back to it at the end of the talk, okay, with my pad if you need more explanation. Okay, so let's X be a Q-Gorenstein compact variety and fix a reference scalar form omega x. Then the Ricci curvature form of omega x could be defined like this. So it's the curvature of phi, where phi is a smooth metric of kx, which is chosen or adjusted so that mu phi, the metric that we have defined earlier, is equal to omega x to the n. So this is not the way I have defined the Ricci curvature in the smooth case, but it turns out to be actually equivalent. And with this definition in hand, we will say that the Kaehler metric on such a mildly singular variety is Kaehler-Einstein if, I cannot even read my slide, if it is the Ricci form is proportional to omega x. So same definition, but once we have the appropriate notion of Ricci curvature form. Okay, so what can be said about solving this Kaehler-Einstein equation in this singular context? Well, yeah, sorry, one small remark is that as in the smooth case, you cannot hope to solve this equation unless the first Chant class has a definite sign. So as in the smooth case, you have three cases to consider. So first, the easiest case, so when the proportional factor lambda is negative. So this is a result, well, due to many people with various steps in the degree of generality. So let's X be a projective variety with log terminal singularities and assume that Kx is ample. So you're working on a canonical model, if you like. Then there exists a unique Kaehler-Einstein metric that we call current here. So with negative Ricci curvature. And this metric is a smooth Horner scalar form on the regular part of the manifold. And as you approach the singularity, you have a globally bounded potential. So this Ricci curvature is a Horner's smooth metric on the regular part, but globally, you can make sense of it globally as you approach the singularities as a positive current. And here, what this statement, for instance, says, which is a bit stronger than just being a current, is that the local potential of these currents are bounded as you approach the singularity. Okay, for your question? Okay, so moving on to the zero curvature case, we have the following results. So assume X is this mildly singular Kaehler variety, compact Kaehler variety with zero first Chant class. Then, well, we have the same result as in Yao's celebrated theorem, namely, if you pick any Kaehler cohomology class, then in such a class, you can find a unique Ricci flat Kaehler-Einstein metric. current, which is a honest smooth scalar form on the regular part, and which has globally bounded potentials as you approach the singular locus. And finally, and as you see, there is a jump in time. So in the case of singular Fano varieties, the so-called Q Fano varieties, then the same type of statement as I mentioned in the smooth setting holds. So this Yao-Tian de Natanz conjecture holds in the context of Q Fano varieties. And this has been achieved in a series of works by many authors, but I'm emphasizing the last main two pieces provided by Berman, Buxom, Johnson on one hand, and Li Tian Wang on the other hand. So both papers are about to appear. I think the first one in Journal of the AMS, and in the next volume of the AMS, and the second one in one issue of the Communication on Pure and Applied Math this year. Okay. So what about the translation of this problem into a complex Monge-Ampère equation? Well, once again, you can, with the same type of reasoning, show that solving the singular Canonical equation is equivalent to solving the following complex Monge-Ampère equation. But as you noticed, on the right-hand side, you have now this adapted measure mu phi. So you can resolve the singularities, and then you pull back this Monge-Ampère equation on the smooth model X prime, and it becomes omega plus ddc phi to the n equals e to the minus lambda phi mu, where you should, let me emphasize that there are two main differences with the previous Monge-Ampère equations that we have been considering, namely, the reference form omega is the pullback of the scalar form omega x. So on the smooth model, it is semi-positive, and it has positive volume, but it vanishes along the exceptional divisor. So it's no longer Kaehler. And on the right-hand side, the measure mu that you capture is absolutely continuous with respect to some smooth volume form. And the density F is LP for some P bigger than 1. The bigger the P, the better the analysis, but this depends on the nature of the singularities. So for instance, for canonical singularities, you can take P equals plus infinity. But for log terminal singularities, P is just a bit bigger than 1. This is the finite mass or a consequence of the finite mass, algebraic finite mass condition. So let me emphasize that obviously the right-hand side is a bit degenerate and the reference form is lacking positivity. So this makes the analysis a bit complicated, but nevertheless, one can solve these equations, and there are several methods that have been developed in order to do that. So one of them, which seems quite natural, is to use smooth perturbation of this equation. So you consider omega is lacking positivity, so you add epsilon omega x prime in order to work with a form which is strictly positive. Mu is not a smooth volume form. Okay, you use maybe convolution to consider mu epsilon, which approximates mu. You try and solve such an equation and pass to the limit. So clearly, this requires to produce a priori estimates. And this is what we have been doing many years ago with Philippe Sidieux and Ahmed Zeriai. And as in the smooth setting, the most delicate estimate is the L infinity a priori estimate, and this is the one I'm going to discuss tomorrow. Another method a bit later has been developed, which is a variational method. And well, in one word, this consists in finding good functionals whose critical points are the solutions you are trying to construct. and studying these functionals and showing that they have convexity type properties and that and properness or coercivity properties. I will say one more word in 2 slides from now about this. And this variational method is the key to the extension of the Yaotian-Donaldson conjecture to the singular setting. So the work of Berman, Buxom, Johnson, and Chi-Tian Wang that I mentioned relies on this variational approach. A slightly different method has been developed also with Philippe Sidiou and Ahmed Zahid. This is a viscosity type approach. And this consists, if you like, in a rough way, in using the classical Perron method of taking envelopes of sub-solutions. This does not always work, but I would say one word about this in the sequel. And finally, and this will be the topic of my 3rd lecture, and also this is the main topic of Valentino's lectures, you can use a parabolic approach. So in order, instead of solving directly by perturbation or whatsoever this degenerate elliptic equation, you can try and approach the elliptic setting, degenerate elliptic setting, by using a parabolic deformation. So this is inspired by the Kaehler flow approach, and I will discuss that on Friday. So a few extra words about each method, except maybe the last one, which I keep for Friday. So this key L infinity a priori estimate is provided by the following statement. So assume X is compact Kaehler of dimension n, omega is no longer Kaehler but semi-positive, merely semi-positive and big. Lambda is a non-positive real, and F is this density which is normalized and in LP for some p bigger than 1. Then the a priori estimate is the following. If phi is a bounded solution of this complex Monge-Ampère equation, then there exists a uniform bound on the oscillation of phi by a constant which you will see tomorrow morning is actually very explicit. So in particular, you can follow this constant along the smooth deformation path and make sure it remains bounded. Okay, so this will be the topic of tomorrow morning. One word about the variational approach. So the starting point is this observation, which goes back, I guess, to the work of Aubin, that if you consider this functional E, which is usually called the energy functional, well, if you differentiate E along the path phi t, then what you obtain is the normalized Monge-Ampère operator of the potential phi. So here V is the total volume of X with respect to omega. And another functional is when you add to this functional E this logarithmic contribution. You should understand this Ding functional. When lambda is equal to 0, you can take the limit of this quantity as lambda goes to 0, and you will end up with minus the integral of phi against omega n divided by V. And it turns out that omega phi, so Ding is invariant under translation. So Ding lambda of phi plus a constant is the same as Ding lambda of phi. So it's actually a functional that acts on matrix rather than on potential. And omega phi is a critical point of this functional if and only if phi is a solution to the complex Monge-Ampère equation. So this is an exercise basic exercise in calculus of variation. So compute the Euler-Lagrange equation of this Ding functional, and it will tell you this. And one insight, if you like, that the negative curvature case is easier than the Fano setting, that this Ding functional is always coercive. So you always have a strong properness property of this functional, which allows you to solve the the corresponding Monge-Ampère equation. So with the properness, this strong properness property, you can produce critical point. Critical point gives you a solution of your Monge-Ampère equation, hence a Canonical equation. This is always possible when lambda is non-positive, and when lambda is positive, so for the Fanon setting, this is not always possible. And for lambda equals 1 by normalizing. For arbitrary Kaehler classes, well, the story is not totally clear. But when the Guedj class is the first-chance class, well, this is precisely the Yaotian-Donaldson conjecture, or singular version, if you like. Okay. One word about the third method. It relies on the following property, which is rather simple, and I can leave it as an exercise when everybody is smooth and positive. The observation is that if you have such a differential inequality in the smooth setting, then U has to be greater or equal than V. So this is a monotonicity property, if you like, so-called comparison principle, or another type of maximum principle. And this leads naturally this makes one think that the Perron method should be applicable in this context. And this is indeed the case. Namely, you can consider the envelope, the supremum of all these functions U, which are sub-solutions of the equation. So the Monge-Ampère of U is greater or equal than the right-hand side. And if you do that, well, you actually construct the solution of the equation. This is not very difficult to realize because in what is called the ample locus, if you prefer, on the regular part of the variety, then omega is a honest scalar form, and you can do local analysis in order to construct local subsolutions. And in that way, we can get easily a solution which is locally bounded in the regular part of the variety. Then the difficult part of the job is to prove that you have a global bounds as you approach the singular locus. So this is some extra work to be done. Okay, this is what I wanted to say, I guess, for this first lecture. And let me finish by giving you a few references. So what I explain is covered essentially by this book that I wrote with my collaborator Ahmed Zahiri from Toulouse, but of course modulo the most recent results that I mentioned, especially this paper by Berman Luxon Jönsson and this paper by Litian Wang. Okay, so I will stop here. Thank you for your attention.
Thank you very much, Vincent. Let's clap for everybody. Are there questions, comments? So if you want, please unmute the microphone and ask a question. Since it's not the case, so I thank Vincent again. And,
sorry, if I could ask a very silly question. Could you please explain again the criterion for the singularities being log terminal, the analytic criterion that that was the content of a lemma? In the notation of that lemma, what was E or EI?
So EI were defined a bit earlier here in the definition. So when you pick a log resolution of the singularities, then on the smooth model X prime, you will get exceptional divisors EI that live above the singularities, okay? And they show up with a certain multiplicity, which is called a discrepancy, which are this rational number AI, okay? So if you now go back to the volume form point of view, what it means is that when you pull back this measure mu sigma on the smooth model, then you peak in the volume form, you peak contribution from these divisors EI, which show up if the local equation is given by EI is Zi equal to 0, then you pick a density which is modulus of Zi to the power 2AI. And this contribution is an integrable if and only if this rational number AI is not too negative. So the obvious critical bound is AI equal -1. So if AI is strictly bigger than -1, and then the mass of this measure is finite and conversely. So that this is precisely the definition of log terminal singularities. Okay?
Okay, thank you very much. Yes, thank you.
So other questions? Okay.